Okay, this is the second video in the sequence of computing Fourier series for a square wave. In the first video, just to refresh your memory, we found both of these integral terms, and now we're ready to do some simplification. So we'll go to the second term that we found and look at this one first. Some interesting things occur here. If I look at this e to the minus jk 2 pi, k, you'll recall, is always an integer. It could be negative, but it could be positive, but it's always an integer. And so you'll recall that this complex exponential, in fact, I'll actually write it down the first time because this is going to be key to understanding what's going on. Actually, that should be a negative sign. Okay, so that's this beautiful hot pink thing here is what this complex exponential looks like. And you'll notice I have an integer times 2 pi. So I'm taking the cosine of, say, 2 pi, 2 times 2 pi, 100 times 2 pi, but it's some integer multiple of 2 pi. And the cosine of an integer multiple of 2 pi is equal to 1. Similarly, I have the sine of an integer multiple of 2 pi, and the sine of an integer multiple of 2 pi is 0. So it turns out then that this integral can be written as 1 over j k pi times this guy, which is 1. And now we'll have to make this go away. Minus e to the j k pi. So all of a sudden things have gotten quite a bit simpler, but they'll get even simpler still, at least eventually. If I look at, well, and I missed a minus sign here. If I look at e to the minus jk pi, again I can write this as a cosine k pi minus j sine k pi, and I recall from trigonometry that anytime I have an integer multiple of pi and take its sign, that's 0. Anytime I have an integer multiple of pi and take its cosine, it's either going to be 1 if k is 0, the cosine of 0 is 0. If k is 2, the cosine of 2 pi is 1, and so on. Did I say the cosine of 0 is 0? That's not true. The cosine of 0 is 1. The cosine of 2 pi is 1. And so this cosine will be equal to 1 if k is even. And if k is odd, then I have the cosine of pi or the cosine of 3 pi or something like that. And that would be negative 1. So if k is odd. So what I have then is in this chunk here, I'm either subtracting 1 from this one or negative 1 from this one. So if k is even, I have 1 minus 1. That's what I have here for k is even, which is 0. When k is odd, I have 1 minus negative 1, which I have here. And that ends up being 2. So this 1 minus e to the minus j k pi is either 0 for k even or 2 for k odd. Okay, so what that means is that this term in our integral I can actually write very simply now as being 2 over j k pi when k is odd, or 0 when k is even. Green was sort of a goofy color to choose there. We'll box this with a little turquoise, make it stand out. So there you have it. That's one of the simplifying results that we get. If we go back to our other integral that we had here, we'll discover something similar in this case. So e to the minus jk pi, again this is cosine k pi minus j sine k pi. This term is always 0. This term, as we just discussed, is going to be 1 when k is even and minus 1 when k is odd. Okay, so when k is even, I will have 1 put into here, and I'll have 1 minus 1. So when k is even, I have the situation where this difference is 0. When k is odd, I plug this in here, and I have minus 1 minus 1, which is negative 2. So the end result of this is that this is equal to minus 2 over minus j k pi when k is odd, and 0 when k is even. Okay, and I can simplify this a little bit by just crossing out these minus 2's, or the negative signs here. Okay, so it turns out that we get the same result here as we had in the other term in the integral. So we can go back to our original square wave, and we can now say that this guy is going to be 1/2 times 2 over j k pi plus 2 over j k pi, and this is the case where k is odd, or it will be 0 when k is even. Okay, so let's see if we can't just get rid of all of this derivation and summarize what we have there. So c of k is going to be 2 over j k pi when k is odd, or 0 when k is even. Okay, actually we should have a curly brace here. So, what this tells us is that our c sub k's are completely imaginary. They have no real component. They have only imaginary components. If the c sub k's are imaginary, then that means that we must have an odd function. And in fact, if you look at this waveform, it is an odd function. X of t is odd. So that makes sense. I have only odd harmonics in this square wave, and in fact, if I start trying to graph what these harmonics will look like, the fundamental harmonic will end up looking something like this, or the fundamental frequency. Then I'll have a term that is smaller in amplitude that looks like this, and so on. Okay, so that concludes this example of how to compute the Fourier series coefficient for a square wave. It turns out that in this case, because our square wave is odd, we ended up with imaginary coefficients. If we were to change the phase of the square wave, so if we were to take the square wave and slide it over a bit so that it looks like this, that's an even square wave, and so it turns out then the Fourier series coefficients would be even. In a subsequent video, we may or may not actually work that case. So anyway, that concludes this video.